Welcome to this exercise that relates to the lecture we have on moisture transfer in pores. This is exercise 2 on moisture retention and moisture transport in a bundle of tubes that we use as a simplified representation of a real building material. So in exercise 1 we were studying the retention of moisture and absorption of moisture. Today it's about the transport of moisture through the porous material. This representation, we have a sequence of pores of varying sizes, as it says here in the table. And when moisture comes into a material, the smallest pores begin to be filled first, and gradually larger and larger pores as the whole conditions get more humid. So the small pores will be filled with water, and transport is in liquid form in those pores. In the still open pores, we have water vapor transport, so it's diffusion of water vapor in those. And those two transports then function in parallel to one another, and we can put some formulas to know about the two forms of transportation. So our ambition is to develop a graphical representation of how the permeability for water vapor and for liquid, how it develops, and we'll show two curves, how it develops in terms of as a function of the moisture content U in the material, but also as a function of the capillary pressure in the water. So it relates to some of the things that we were talking about in the lecture. So here I show two slides. The first one tells about the liquid transport, and in the lecture we used the Hagen-Poiseuille equation, which for one tube with a certain radius and a certain length will give this transport when we have a pressure difference in the capillary pressure difference from one end to the other of the pore. We could also put it in a differential form, so for an infinitesimal length, this becomes a similar equation according to the Hagen-Poiseuille's law. So we have to use this, the radius of the pore, and we also have to look to the dynamic viscosity of the liquid in the pore. Now, everything boils down to what is here in red, and I'll not talk about it very much in detail, but just to say that everything in red here can be gathered in this transport coefficient, the liquid permeability that we are aiming for. So this is the formula that we will use when we make the calculations. Now, that was for the liquid part. We have a similar slide, as I indicated before, for the vapor diffusion part. So if we have a pore of a certain pore radius size, then we have transportation from one end to the other by vapor diffusion, and we can have a little bit some analogy and writing up some equations like that also. Vapor diffusion, we have talked about in another part of the course, that we can represent this in a way that although physically the water vapor pressure is a driving potential, it can, via the Kelvin equation, be represented as a capillary pressure. So to make as we will do today, a permeability that refers to capillary pressures but talks about vapor diffusion, well, then we can see the conversions that are needed here, and I'll not talk in detail about this because that's in the lecture, but here is in the frame the formula that we'll need to tell us what is the permeability for water vapor transport. So that's what we're going to use now when I skip over to show to you I have to find it here, the spreadsheet that gives us the solutions. Now I just showed you the result, but let's lead us through it, how to come to that one here. So first of all, we have for the liquid permeability for one pore of a certain size radius. So when we have double asterisk here, it refers to one size of pores only. So this gives us the liquid permeability for one pore only. Then also for the vapor, the equation that we saw in the end when I showed the PowerPoint slides before, well, then we make this unit here that we're looking for that refers to the suction pressure as driving potential, derives from the water vapor permeability, the conventional water vapor permeability of water vapor in air. So that is to consider vapor diffusion in the still air-filled pores. We need for the calculation, we need some physical parameters. Only thing I'll just refer to here, just to remind you about that, is that we have a number here which tells us what is the moisture content in the material when it's completely saturated, so when all pores are filled. Then from geometrical configurations, the volume that we have in the material and the weight of that water, we will know how much moisture content kilogram per kilo we have in that situation. So the rest will have a definition kind of relative to this size here. So now I'll scroll down in the spreadsheet to where I have the calculations. And I have here columns, one column for each size of pores. So this was for the smallest pore I had in the bundle here. By volume, they fill 2% of the total volume of the pores in the material. So when the saturated moisture content for the fully saturated material was this much, then the moisture content in this situation here is only 2% of the total value here. Okay then, but I'll just go up further again to say that for this pore radius, then with the surface tension of water in such a pore, we have also talked about that in the course, then we have this capillary pressure in the water that stands in such a small pore. So that's what we'll refer to or use. But since the capillary pressure develops very much has a very rapid development, then we very often plot it by the logarithmic to that value. So that's what we're also going to use. The Kelvin equation makes it possible to calculate from capillary pressure to relative humidity over such a water-filled pore. So that gives us the relative humidity that will be in the air just over such one water-filled pore here, 11.8%. So now, and we have, as I talked about before, we have the moisture content in one pore of that size. Now we can do the next four, also the next size of the pores, the one that was a little bit bigger and bigger and bigger and bigger. And we want to have the accumulation of what happens when gradually starting from the smallest to that we fill it up. So the next row here simply makes the summation. So we take this value plus the addition, gives us this value we have here. And so forth, we can continue all the way along all the pore sizes. So this is the summed up moisture content in our material as it all gets filled up. Now, then we can go to that equation we had on the top that tells us for this one pore, what is the liquid permeability of that pore. This is the number that we could calculate for this one. When the next pore also gets filled up with water, then it has this permeability, and the total permeability of the material becomes now the sum of the ones that we have, the smaller ones here, plus the next one here. So that's what the equation says here, how to calculate. And then we can sum it up for all the ones that we have. That was for the liquid. Now for the vapor transport, well, this is the vapor transport for an empty pore of that size. Then we have this water vapor permeability for if that were the only pore that we had. We can do it also for the bigger pore, for the next one and the next one and so forth. So as always, the total or the summed up permeability becomes the sum of what we had before and the next one here. So that's how we sum it up. Only thing is that for the vapor, when first of all, that was how the formula worked from before, how we summed it up. When we have first the liquid parts begins to fill the smallest pores, then it means that as liquid comes in the smallest pores, then the big pores are the ones that are left with the vapor. So gradually, as liquid comes in the smallest, there will be less and less that are water vapor filled. So that's how this function here, where we sum it up, that we sum it up kind of to the right of, so all this, the bigger pores from where we are at the moment. Now, in the bottom down here, then we have for the vapor, we have that calculation from the normal, if I may say, water vapor permeability, using that formula we had on the last slide, how it translates from water vapor permeability into a value kV that is the same number, but referring not to water vapor pressure, but to the capillary pressure as our way to represent water vapor content in the material. So that is kV, that it was one of the values that we should plot, and before we calculated KL down here in this row here that we should plot. Now, coming towards the end, I will, of course, not only talk about calculations and numbers, but let's see the results. So first, here is a plot of the liquid permeability for that's the blue curve here, as it develops with the moisture content in the material. And the red curves is the vapor permeability in the same units. And we can see how it declines as in the end, all the pores are getting filled with water, and therefore there's in the end no vapor diffusion in gas phase possible anymore. So now we have the total representation of the two separate transport forms plotted in this graph versus the moisture content. And last question that we should solve was to plot the same results, but now versus the capillary pressure. And it's the same results, but also the abscissa axis is different, and also the direction is opposite. So here this represents kind of a dry situation, and this represents a more moist or humid situation, if you will. But in principle, these are the same results. So those were the two results that we should plot here in this exercise. That completes the whole story. In Danish, we could say, så får I ikke mere for den 25 øre. And that translates into, that's all, folks. So thank you for now.